The electricity traveling through the transmission lines outside your window is a high-voltage alternating current, often pushing thousands of volts. But the processor inside your smartphone requires something completely different, a tiny, stable direct current, usually at less than 2 volts. While the grid is highly regulated, its output is built for long-distance transmission, not delicate microprocessing. You can't simply plug a sensitive chip into a high-voltage AC line. The mismatch in voltage levels and current types means that without a translator, the raw power would instantly destroy the device. This is the core mission of power electronics. It uses solid-state semiconductor switches to manage the flow of energy, stepping down voltages and converting waveforms until the power that emerges on the other side matches the device's specific requirements. This chart outlines the scope of the field, categorizing converters into 4 primary roles. We use rectifiers to turn AC into DC, inverters to do the opposite, DC to DC choppers for voltage scaling, and AC to AC controllers for frequency and voltage adjustment. These invisible switches act as the essential interface between the high-power world of energy generation and the low-power world of modern computing. Without them, the energy grid cannot communicate with the devices that run our lives. The simplest way to dictate electrical flow is with a power diode. It acts like a one-way valve for electricity. It forces current to flow in a single direction, but it offers no active control. It's strictly an uncontrolled switch dictated entirely by the circuit's natural physics. To gain active control, engineers use a silicon-controlled rectifier, or SCR. This is a semi-controlled device. By adding a third terminal, called a gate, we can send a small signal to command the switch to turn on exactly when we want it to. This graph illustrates the SCR's voltage-current characteristics. In the forward blocking state, the switch is off. When we apply gate current, labeled IG, it snaps into conduction. But the SCR has a limitation. You cannot command it to turn off. It only stops if current falls below the holding current. For alternating current applications, engineers use specialized components like diacs and triacs. As shown in this equivalent diagram, they function essentially like 2 diodes connected in opposite directions, creating a perfectly symmetrical structure that can trigger and control power in both positive and negative polarities. These semi-controlled devices are rugged enough to handle heavy industrial motors and power lines. However, because they lack the ability to be actively turned off at high speeds, they are unsuitable for precise, high-frequency electronics. That need for speed and precision led to fully controlled devices, most notably the power MOSFET and the insulated gate bipolar transistor, or IGBT. With these, engineers can actively command the switch to turn both on and off entirely at will. Inside a power MOSFET, applying a positive voltage to the gate terminal generates an electric field. This attracts electrons to the surface, forming a thin conductive bridge called an inversion layer. Once that channel forms, current can instantly flow from the drain to the source. Looking at a MOSFET's output characteristics, we see how this gate control works. By varying gate voltage, the device acts as a hard on-off switch in the saturation region, or operates in the ohmic region shown here, functioning like a variable resistor. Because they don't wait for current to naturally drop to zero, MOSFETs can chop and switch electrical signals millions of times per second. That extreme switching speed is what enables the compact, high-frequency power supplies driving all modern computers. But even the most advanced silicon switches hit a physical wall. Every single time a device turns on or off, it encounters slight internal resistance, causing what engineers call switching losses. When switching a massive electrical load millions of times a second, those tiny moments of resistance add up, converting wasted energy directly into intense heat. To keep the semiconductors from melting, this diagram shows how thermal management systems pull heat away from the component. They rely on thick metal heat sinks to absorb the energy through conduction and then dissipate it into the surrounding air through convection. This creates a hard physical bottleneck for modern technology. We can't shrink our power adapters or industrial converters any smaller because a standard silicon chip requires a cooling system that takes up a massive amount of physical volume. To break past the limitations of silicon, the electronics industry is moving to wide bandgap materials, specifically silicon carbide and gallium nitride. This table compares standard silicon to gallium nitride. Notice the electron mobility row. Electrons move faster through GaL, allowing vastly higher switching frequencies with near zero power loss. Moving up, these materials possess higher band gap energy. Silicon carbide leverages this to withstand extreme voltages and temperatures without failing. Because these new materials waste so little energy as heat, the massive metal heat sinks and magnetic components can be stripped away. This is exactly how your new laptop charger shrunk to the size of a golf ball, and how electric vehicles are packing more power into lighter drive units. When you look around at the shrinking hardware on your desk, or the increasingly sleek technology in our infrastructure, you are watching the physical results of this semiconductor transition. Solar inverters can now harvest sunlight with greater efficiency. Electric vehicles are physically shedding weight and extending their driving range because their onboard chargers run cooler and require significantly less space. Building a sustainable grid relies heavily on generating cleaner electricity, but it equally depends on controlling that electricity with absolute precision and zero waste. Power electronics form the solid-state foundation of our infrastructure. They are the essential translators that make the transition to a fully electrified future physically possible.